Hello everyone. In this lecture we are going to discuss change to polar, and here we have to convert our Cartesian coordinate system xy into the polar coordinate system r and theta. And we know that for this there is a standard substitution, that is we have to replace x by r cos theta, y by r sin theta, and dx dy by r dr d theta. Now depending on that we are solving an example, and the example is change to polar coordinates and evaluate the double integral from 0 to a upon square root 2 and y to square root of a square minus y square log to the base e of x square plus y square dx into dy. Now first of all we are writing this double integral in details. That means we can observe this inside integral limits both are the function of y, and therefore for this inside integral our x is varying, so that we can write this integral as x equals to y to x equals to square root of a square minus y square. Similarly, this outside integral is moving constantly, so that for this integral our y is varying, so that we can write this outside integral as y equals to 0 to y equals to a upon square root 2, and the remaining part, that is log to the base e of x square plus y square dx into dy as it is. Now first of all we have to decide our region. Therefore the region of integration is bounded by x equals to square root of a square minus y square, that is upper bound of or upper limit of this inside integral, x equals to y, that is lower limit of this inside integral, y equals to 0, that is lower limit of outside integral, and y equals to a upon square root 2, that is upper limit of outside integral. So these all curves gives us a region of integration. Now first of all we are plotting these curves on the graph. Before that we can observe this first equation, x equals to square root of a square minus y square, I can write as x square plus y square equals to a square by taking squaring to both side, and by taking this minus y square to LHS side we'll get this x square plus y square equals to a square. And we know that this is the equation of circle centered at origin with radius is a. Similarly we can observe the second curve, that is x equals to y, it is nothing but a line passing through origin, and y equals to 0, that is nothing but whole y-axis. Similarly y equals to a upon square root 2 is a line parallel to x-axis. Now first of all we are plotting all these curves on the graph, and if we plot then this will be the figure. So in that we can observe this circle is nothing but x square plus y square equals to a square, which has centered is origin and radius is a. Similarly the second curve, that is x equals to y, is nothing but straight line passing through origin, and y equals to 0, that is whole y-axis, so that is y equals to 0, and y equals to a upon square root 2 is nothing but line which is parallel to x-axis. Now there is one intersection point, this is the intersection point which can be found by using the equation of line and equation of circle. Now according to the lower limit and upper limit of the both the integral, this shaded region is nothing but our region of integration. That means for the variation of x in inside integral, our x equals to y line is the lower limit, that is lower bound, and this x equals to square root of a square minus y square, that is the equation of circle, is the upper limit, that is upper bound for the x variation. And similarly y equals to 0, that is this x-axis, is the lower limit, that is lower bound for the y variation, and y equals to a upon square root 2 is the upper limit, that is upper bound for the y variation. So this shaded region is our region of integration. Now our target is to find the double integral using that region. But before that we have to change our Cartesian coordinate system into the polar coordinate system. So first of all we are converting all these curves into the polar coordinate system. So if you consider our first curve, that is x square plus y square equals to a square, then by replacing x by r cos theta, y by r sin theta, we'll get r cos theta bracket square plus r sin theta bracket square equals to a square, and after squaring and adding we'll get r square common. In bracket only cos square theta plus sin square theta is remain, so the value of cos square theta plus sin square theta is 1. So at LHS side only r square is remain, so r square equals to a square. This will be r equals to a in positive quadrant. So the same equation I can write as r equals to a in polar form. Similarly, we can write this second curve in the polar form as r cos theta equals to r sin theta, implies that r will get cancelled, so sin theta upon cos theta equals to tan theta and equals to 1. So it possible only when theta equals to pi by 4. So this x equals to y equation I can write as theta equals to pi by 4 in polar coordinates. Similarly, y equals to 0 I can write as r sin theta equals to 0, and obviously this sin theta will get 0 only if theta equals to 0. So theta equals to 0 is the polar form of equation, and the last curve, that is y equals to a upon square root 2, by putting y equals to r sin theta, then r sin theta equals to a upon square root 2, so it implies that r equals to a upon square root 2 into sin theta. So these are the polar form of equation. Now using that all polar equations, we are plotting the another figure which is exactly similar to the first figure. Now in that figure I have written every equation in polar coordinates. That means equation of this circle is r equals to a, that is polar equation. Similarly, this x equals to y line I can write as theta equals to pi by 4. This line, that is y equals to a upon square root 2, I can write as r equals to a upon square root 2 into sin theta. Similarly, this x-axis, that is y equals to 0, I can write as theta equals to 0. Similarly, we know that at this line, at the upper side of y-axis is theta equals to pi by 2. Similarly, here theta equals to pi, and at lower side theta equals to 3 pi by 2. Now our next target is to find the limit of r and theta, and we are finding that limits using that region. So first of all, I am considering one radical strip which is starting from this origin and ending at this curve. Therefore, according to that radial strip, our radius is starting from this origin and ending at this curve, that is equation of circle, that is r equals to a. Therefore, our r is moving from r equals to 0 to r equals to a, that is the limit of r. So I am writing this variation of r here, that is r varies from r equals to 0 to r equals to a. Now we are finding the limits of theta. Now obviously for this region our lower side is this line, that is theta equals to 0, and for this region our upper side is nothing but this line, and equation of this line is theta equals to pi by 4. Therefore we can say that the lower limit for this theta is theta equals to 0, and upper limit for this theta is theta equals to pi by 4. Therefore the variation of theta I can write as theta varies from theta equals to 0 to theta equals to pi by 4. Now we got the limit of r and theta. Now using that limits we are finding the double integral. Therefore given double integral can be written as I equals to 0 to square root of a upon 0 to a upon square root 2 and y to square root of a square minus y square log to the base e of x square plus y square dx into dy. Now I have to change this Cartesian coordinate system into the polar, so that I have to take a limit in terms of r and theta. So according to our limits, our first integration moving from theta equals to 0 to theta equals to pi by 4, and another limit that is from r equals to 0 to r equals to a. Similarly, we have to change our inside part also, that is we are replacing x by r cos theta, y by r sin theta, and dx dy by r dr d theta, that is using our standard substitution. So if I put x by r cos theta, then it will get log to the base e r cos theta bracket square plus, instead of y we are putting r sin theta, so this will be bracket of r into sin theta bracket square. Instead of dx dy we are putting r dr d theta. So you can observe this whole double integral is in terms of r and theta. So now we are solving this double integral. So first of all we are taking integration with respect to r. Before that we are simplifying this term. So if we simplify this, we'll get only log to the base e. Here if you can take r square common, so in the bracket cos square theta plus sin square theta is remain, and the value of this is 1. So log to the base e of r square I can write as 2 into log of r. So 2 into log of r, and this r will be as it is. So the simplification of this whole terms is 2 into r of log to the base e of r. Now in the next step I am taking this 2 to outside the integral, and for to find the integration of this r log to the base e of r with respect to r, I am using integration by part. So according to the our LIT rule, our log to the base e is the first term and r will be the second term. So first of all, by using the by part rule, that is this integration by part u into v rule equals to log r, that is our first term, and integration of this second term, that is integration of r, is nothing but r square upon 2 minus integration of or derivative of our first term, that is derivative of log r, is nothing but 1 upon r into the first time integration of this r, that is r square upon 2, and its whole with respect to r integration. So after solving this term we will get log to the base r, log r is as it is into r square upon 2 as it is minus, now here one r will get cancelled, so only r upon 2 is remain, and integration of r upon 2 with respect to r is r square upon 4. Therefore this is the simplification of this, and now r equals to a and r equals to 0 is upper and lower limit of this r. So in the next step we are putting upper limit and lower limit. So if I put upper limit, that is r equals to a, then I will get log a as it is. Instead of r we are putting a, then it will get a square upon 2 minus r square, that is a square upon 4. And if I put lower limit, that is r equals to 0, then instead of r this will be 0 minus this will be also 0, so whole bracket will be 0 if I put lower limit, and therefore this will be the only term. Now we have to take an integration of this with respect to theta, but there is a no theta here, so all these terms will be the constant when we are taking integration with respect to theta. Therefore I am taking this whole term to outside the integral, so the remaining terms in the bracket is only 1. So integration of this with respect to theta is theta only, and theta equals to pi by 4 is upper limit and theta equals to 0 is the lower limit, and this constant terms will be as it is at LHS side. So in the next step we are putting upper limit, that is theta equals to pi by 4, then it will be pi by 4 minus, if I put lower limit then it will be 0. So after multiplying this whole term by pi by 4 we will get pi into a square upon 4 into log a minus 1 by 2, and that is our final answer. Thank you.